when we have a number of charges and we want to find field at a point, then we will consider field due to each. Let's say these are the charges and we want field at this point. We will consider field due to each, due to this alone, due to this alone, due to this alone. And then we will find the vector sum of the three fields, giving us the total field at point P. It is just like vector summation. When we deal with continuous charge system, then this way converts to integration. But then vector integration is going to be more difficult. So we look at some symmetry. Symmetry helping us with components, and certain components cancel out, and then we integrate. Otherwise, when you are dealing with vector, integration may not be easy. So first break the vector into components, cancel as much as you can, and then you can integrate. If vector addition starts behaving like scalar addition, as you know, sometimes in vectors 3 plus 2 is 5. When the vectors are in the same direction, then 3 plus 2 is 5. So when only those vectors are remaining for which 3 plus 2 equal to 5 type of thing works, then you can integrate. So I will give you illustration. We want to find field due to a ring. On the axis of the ring, at a point distance x or d if you like from here, center. It is a uniform charge distribution, the total charge being capital Q. Radius is A of the ring. It is uniform charge distribution. So imagine Q1, Q2 type of thing. Here we will take dq. Put a test charge positive. Let this capital Q be positive, repulsion. So the field will have this direction. Because it is due to a small dq charge, only this much, let it be dE, but it's a vector. And that dE is given by k times dq divided by this distance square, which is a square plus x square. Are we justified in using the formula valid for a point charge? Yes, we are. This is such a small distance, it is like a point charge, dq. It is like a point charge, so we are justified. Now I was saying about integration. This is the key step. You can't do this integration, because other d's, integration is addition, right? And other d's, if you look at, then they are not in the same direction. When 2 plus 3 equal to 5 works, then you can integrate. Right now 2 plus 3 equal to 5 is not working. This is d in this direction, this d is in this direction. Several d is in several directions. How can 2 plus 3 be equal to 5 for such vector addition? So we take components. Symmetry will be the key. Symmetry will be the key. Look at another dq here. And due to that, d will be like this. It is also the same dq only. So same d. And now you can see that this component and this component, the two components will cancel out. Likewise, for every dq that you take on the circumference of the ring, you will find a partner, or whatever you like to call it. Let's say pair. We'll be able to find pairs. And this with that, this with that. Everybody will have some partners, or there will be pairs, suitable pairs, such that only one component will survive, and that is the axial component that will survive. So for everybody who survives, for this d who survives, axial component. For this d who survives, axial component. Likewise for this dq, whatever d is there, its axial component will survive. Right? Now when we understand it, we can delete this. And we can just say that only the axial component will survive, and everybody has the same direction. This d also, component this direction. This d is component in this direction. Due to this, whatever d is there, that component same direction. If vectors are in the same direction, 2 plus 3 is 5. That means now we can integrate. We could not integrate this fellow, but we can integrate this component, and that component is d cos theta. So while this is correct, putting integral sign over here would not be correct. Any questions up to this point, let me know.
Sir, where should the integral sign not be put?
Yes.
Fine, sir.
We need to remove cos theta. It is outside, x is fixed, radius is fixed. Sometimes use of x creates this problem that it gives you the impression of a variable. That's a sometimes problem with using x. We are talking of a fixed point, field at a fixed point, at a distance x. So that's why I said you can take d also if you want. That d is fixed, this a is fixed. So this whole thing comes out. Then cos theta. Cos theta is x upon under root a square plus x square. Then dq. X is fixed, comes out. This becomes to the power 3 by 2. Well, looks like it's so easy now to integrate. Integration is actually nothing, straightforward. Sum of all charges, Q, capital. So KQX upon this. That's the final answer. Any questions? Let me know. So after doing the ring, another case is of rod. Again, uniform charge distribution. Total charge is Q. Total length is L. We want field at a perpendicular bisector. This is a perpendicular bisector. There is a point at certain distance. Maybe D. So we want field at this point. From here at a distance x, we take very small length dx. Due to dx, the little field d would be like that. Let the little charge in dx length be dq. This d would be given by k dq upon this distance square. Now, we cannot integrate this because d is a vector. When you look at other dq's, you will find these in all other directions. If these are in several directions, how would they add like real numbers? So if we consider pairs, symmetric pairs, this dq here, d there, then we find that components in this direction won't survive. Only components in this direction would survive for everybody. For everybody. So while integration here would not be correct, if you just consider the vertical component, then integration is correct. And if this angle is theta, then vertical component will have cos theta. Now one can integrate. The net field will have this direction. If Q is positive, this arrow will be correct if Q is positive, and then the field would have this direction. But if Q is negative, field would have this direction. Here net field had this direction if this Q was positive, and if this Q was negative, field would be in this direction. So for every dq, d cos theta will survive, and everybody will have same direction of d cos theta. So you can integrate now. In previous case, integration was very easy. Let's see how it is in this case. K is fixed, distance is fixed, but x is not. Okay, this is not going to be that easy, integration here. This is changing. Only k is out. In fact, when we integrate, trigonometry can help us. So let's try to get rid of x and keep this theta. If I don't want x, then I can use tan theta equal to x by d. D square is out. One plus tan square theta is sec square theta. Cos cube theta. Let me recheck. Looking okay, but this is Q. This is Q. So we should get rid of Q also. Q, Q, Q. Now, it is a uniform charge distribution. Charge per unit length will be this. Multiplied by dx. I hope this step is clear. That should be dq. Linear charge density multiplied by the distance, dx. Okay? I don't want x. Okay, tan theta x by d. So x is d tan theta. So dx will be d sec square theta d theta. So k by d square q outside L outside cos cube theta, and dx is d sec square theta d theta. Up to this point, if you have any questions, then let me know. Fine. Now the good news is that sec square theta will cancel cos square theta, and d will come out. Integrating cos theta, sin theta. Now, limits. If you look at the figure, then limits would go from minus some angle, maybe you can call it phi if you like, minus phi to phi. Minus phi to phi. That means 2 sin phi. After putting the limit, this is q. Now, what is sin phi is no problem to tell. Twice kq by dl. Sin phi is L by 2 divided by L by 2 square plus d square, whole under the root. Isn't it? Any questions? If you have, then let me know. That's a standard result. It will work only for perpendicular bisector. It's not going to work for this case, for example. So any special cases will have to be handled as a separate problem. Any questions if you have, let me know. There's also one more standard case, which is of long rod. Long rod. Long rod is quite simple. Imagine L to be so big that with respect to L square, D square can be neglected. So if L is huge, then the result becomes this. And Q by L is charge per unit length. We often use lambda for this. This is another standard result. Call it infinite rod if you like. Practically speaking, rod cannot be infinite. Practically speaking, it is this. L is huge in comparison to D. So any continuous charge system we can handle. Full ring, half ring, 3/4 of a ring, or rod, or any specific thing that we come across. You have seen that how field can depend on the distance with respect to the source of charge. Sometimes we want to create a constant field in a region. And for that, what is called as a parallel plate capacitor can be used. Imagine two huge plates, again huge with respect to what? With respect to this distance, let's say, distance between them. So two huge plates are kept parallel to each other. They have got surface charges, one having positive charge, other having negative charge. This is one of the ways to create constant field that does not depend on the distance. It just remains constant. Of course, not everywhere. Not everywhere. Constant in this region. But inside this region, you don't have to worry if it is close to this point or this point. It is all same everywhere. And its direction is from positive to negative. In this drawing, it would be downwards. Later, when we discuss Gauss's law, then you will understand Why is it constant? Actually, finding electric field discussion is far from over. Finding electric field discussion is far from over. We have found electric field due to point charge using basically Coulomb's law. For one point charge or for system of point charges, and then also for continuous charges by using integration method. But that integration method effectively used Coulomb's law only. Little dq could be taken as point charge. So basically, we have found electric field using just Coulomb's law. Whether discrete charge case or ring case or rod case, finite or infinite, method was one and that only in all cases. That is only part of a technique to find electric field. There are other techniques to find electric field, and a major technique is Gauss's law that we have yet to discuss. There are basically three techniques to find electric field. One you have seen, based on Coulomb's law. Second one, a big discussion, Gauss's law. And third one, from potential. From potential. Potential we will define first, and then we will find out a relationship between potential and field, so that if potential is known to us, we can find the field from that. So there are three ways to find field. Now, I was talking about uniform field due to another reason. And that reason is something like projectile motion in electrostatics is possible if you have such a field, something like projectile motion. Say you have got constant electric field. Constant electric field. And if you fire a charge in this region, just like bullet fired horizontally, earth is pulling bullet down. Exactly like that it happens. So you fire a charge horizontally, just like you would fire a bullet horizontally. If that charge is a positive charge and its mass is so small that you don't have to worry about gravitational field, say a positron for example. A positron has such a little mass that earth pulling it down has marginal effect in comparison to the electrostatic force that it would be experiencing. So many times we neglect gravitational force. So if a positron is fired like that, it will feel downward constant force. That's a constant field. It's just like constant mg, gravitational force, when you fire a bullet horizontally. So what happens to the bullet? Bullet follows the path of a type of parabola and then hits the surface of the earth. Here it will hit the surface of the plate, one plate of the capacitor, like that, bang. or we can design this in such a way that it just misses, maybe just misses. But this will be a parabolic path. As long as it is in the region of constant electric field, the path will be parabolic. But then outside this capacitor, there is no electric field. We are assuming that there is no electric field. So when it comes out from, say, here, then it has got no force acting on it. Neglect the gravitational force. So it will go absolutely straight. So parabolic and then absolutely straight. No bending after that. That's how we have got the motion of a charged particle fired in a constant electric field. And its math is just like the math of horizontal projectile motion. Let's do a problem based on this. Here we are taking electron, and that means it will go up, that type of parabola. And let's say we want it to miss the hitting. So it would go parabolic path up to here and then straight line. And this is a midpoint. So distance between the plates, whatever it is entering at the half, midway. We want to know this angle. Now actually this is not given that it just misses. We will have to find it out if that is the case. So maybe it just misses, maybe it comfortably misses. So let's see if we can answer that question. Will it hit? Will it just miss? Comfortably miss? Let's see. If this is x-axis and if this is y-axis, let's say t is the time in which it reaches the corner, whether the top point or somewhere here. There is no force along x direction. So distance equal to speed into time. Y direction, let's say it has moved up y. It has moved up by y. Now whether y is this or d by 2, we'll see. Now in y direction there is force F equal to ut plus half at square. U is 0. Y is 0, I mean. In y direction no velocity component. Half ay. Acceleration in y direction is force in y direction is QE. So acceleration in y direction is QE by m. Fy is QE. Ay is QE by m. That means y is half QE by m t square. Now time is same for x direction motion and for y direction motion. So I'm going to put in place of t x by v naught. Now let's see, when x is L, when x is L, what is y? Fine. It looks like we can't tell. We can't tell if you put x equal to L, then you can't say that y will be d by 2 or less than d by 2. You can't say that. Y actually does not depend on d at all. L square will come here, E M B naught. No. So we cannot say if it will just just be able to go or will comfortably be able to go. Fine. So we concentrate on this question then. Assuming that one of the two things happen, whatever happens, we concentrate on this, find the angle of deviation. What is the meaning of deviation? Originally, if something is going in this direction, and finally if it is going in this direction, angle between the two is called deviation. So we want this angle. How do we find it? Vx is always v naught. Vx here also will be v naught. And what will be Vy there? Suppose I know Vy there, then I can tell that tan theta will be Vy by Vx. So I should try to find out Vy. That's it. Vx is already known. Vx won't change, right? X direction motion has nothing to do with y direction force. So V0 won't change. Vx won't change. It will be equal to V0 all the time. So let's find Vy. Vy square is uy square plus 2ayy. What is uy? What is uy? Can you tell me? What is uy?
So 0.
0. Ay E by m y. That means 2 by m, and y is this half by m. X is L there, L square upon V0 square. That's it. Vy is known, which is E square, L square, M square, V0 square. So Vy is EEL by M V0. And therefore tan theta would be EEL by M V0 multiplied by Vx. Vx will be naught. So EEL by M V0 square. So theta will be tan inverse of that thing. If you have any questions, let me know.
So when X is less than L, then won't we say that electron won't cross the plates?
We are assuming that it will cross the plate. Find the angle of deviation of the path as it comes out of the field. So we are assuming that it is able to come out of the plate. Otherwise, if X is too small, if L is too small, Y is depending on X square. The problem will be when X is, when L is too large, then it will be a problem. Imagine L is huge. Then what can happen is this. Y is depending on X square, L square that is. That's a problem if L is huge. Then this chance is more that it will go and bang. If L is huge, the larger L is, the riskier it is. So small value of L actually would mean that it has a greater chance of coming out. Smaller L. Greater chance of successfully coming out. So we have assumed that it is successfully coming out, or the problem would not be meaningful. Any other question?
Fine, sir.
You don't have to answer it right now. More than one options may be correct. More than one may be correct. That's your assignment question. We stop now.